Physics. These are the universal gravitation problems that I gave you. 2 free response questions, one from 1999, one from 2001. Good year for space and things like that. But first, 1999. We've got a spherical non-rotating planet, has a radius r and uniform density ρ throughout its volume. Suppose a narrow tunnel were drilled through the planet along one of its diameters as shown in the figure above, in which a small ball of mass m could move freely under the influence of gravity. So that's a situation we have talked about. Let r be the distance of the ball from the center of the planet. First thing they want us to do is show that the magnitude of the force on the ball at a distance r less than r from the center of the planet is given by F equals negative CR, where C is equal to 4/3 pi g rho m. All right, let's see if we can do that. So, part A. We're trying to show gravitational force, and we know that the gravitational force is going to be G m m over small r squared, right? Now the problem here is that this large m, we want this to be the mass of the planet that's only inside that radius of r. So what is that m? Well, it's like a portion of the whole thing. That mass of the planet inside r is like 4/3 pi r cubed over 4/3 pi r cubed times the mass of the whole planet, right? Times that big M. Now notice that that big M doesn't show up anywhere in their calculation. So they want us to use the density. Now remember that density is equal to, that's a measure of mass per unit volume. So the density of the whole planet would be equal to m over 4/3 pi r cubed. Right? The density of the whole planet is the whole planet's mass over the whole planet's volume. Right? So that, notice that that's right here. So the mass inside r is 4/3 pi r cubed times the density. Right? Which should make sense. I mean, that's how much volume we actually have times density. Volume times density gives you mass. So that's another way to think about that. Okay, so now rewriting this equation, so gravitational force is equal to G, our capital M, that's this, times 4/3 pi r cubed rho times small m all over r squared, and that is the expression that they want. And the only thing, I guess, is that we just want to have a negative sign here, right? Because that gravitational force is always going toward the center, and that's always the opposite of that that sign right there. So maybe we should just write that out one more time, clearly without our scribbles on there. So that's minus G times 4/3 pi r rho times m. So there's the, I should have done it in this order. Hold on, let me just fix that. Let's make that the M, make that the R, because then this is that's the C, right? Okay, so part A, mission accomplished. Part B, on the axes below, sketch the force F on the ball as a function of the distance r from the center of the planet. Well, the force is going to always be negative, right, toward the center. So I'm going to make the whole thing underneath. I'm going to represent those as negative forces. And when it's absolutely at the center, it's 0, right? And then when you get to the surface, that's what we found in part A, right? And since it's just equal to negative CR. It's just a straight line. Right? Negative a constant times R, so that just gives me a straight line like that. And then what happens as we get further and further away from the planet? The gravitational force decreases, right, as you get further and further away, and it's an inverse square relationship. So inverses and inverse squares go like this, and it asymptotically gets closer and closer to 0. So something like, right, this at 2r, it should be equal, it should be 1/4 of what it was here, right? Because if you think about the r squared on the bottom of the gravitational force, once you double that radius, it's going to decrease by a factor of 4, and so on and so on. So something like that. Okay? The ball is dropped into the tunnel from rest at point P on the planet's surface. Okay? Determine the work done by gravity as the ball moves from the surface to the center of the planet. Well, as the ball moves from the surface to the center, the work done, it's accelerating, so that would be positive work. And notice here, that's like talking about, I'm not going to draw on this because this is my graph, we don't want to make that mistake. It's when, sorry, let me go back to here. For a variable force, work is equal to the integral of force as a function of distance. I'm using r here instead of x, but it's just because r is our distance variable here. So I'm going from the surface to the center, right? Work is equal to that. That's going to flip the sign. It's going to make it have positive work. But of course, we know that it's going to be positive work because it's going from having no kinetic energy to going like as fast as it's going to go at the center. So that's positive work because it's increasing, its kinetic energy is increasing. So how do you want to deal with that? Well, let's see, we can say that is equal to, we know that force from part A is equal to all this mess, right? So, or you could also do it as the area, since we have this, we know it's going to be the positive area of this triangle. So that's, you could do it one of those two ways. So I'm going to go the area of the triangle way. You could go the calculus route too. Area of the triangle is equal to 1/2. The base of the triangle is r, and the height of the triangle here, that's the gravitational force at the surface, right? Which is just Gmm over r, right? So the only problem with that is we don't have a capital M to use. That's Gm. Did I say over r? I meant to say r squared over r squared. Right. The only problem is, what's that? Well, mass is equal to volume times density, so that's 4/3 pi r cubed times rho. Right? Volume times mass over volume gives you mass. So that's my mass there. So that's equal to 1/2 times r times 4/3 pi r cubed rho. What did I miss there? I just plugged that in for that, and I left out the g and the small m, and that's all over r squared. I'll put that there. So that gives me, let's see, 2 cancels out here, so I have 2/3 pi, there's an r, and there's another r, so 2/3 pi r squared rho g m. I better check that. It's a crazy looking answer, but that's what I got. All right. Determine the speed of the ball when it reaches the center of the planet. All right. the speed of the ball when it reaches the center of the planet. Well, we know that work is equal to change in kinetic energy. And it started with no kinetic energy, so in this case work is just equal to the final kinetic energy. So that means work, 2/3 pi r squared rho gm is equal to 1/2 mv squared, right? And the small m's cancel out, as they often do. Doesn't matter. And then multiplying both sides by 2 gives me v is equal to the square root of 4/3 pi r squared rho g. That's the speed. So it's from work equals change in kinetic energy. Part E, fully describe the subsequent motion of the ball from the time it reaches the center of the planet. Well, this is getting a tiny bit ahead of ourselves into chapter 15, I guess, but not really, because we know that when we have this kind of situation, force equals negative kx, that's what this is, right? And we've talked about this in class. We know that, in fact, what's going to happen is it's going to become what we will come to call in chapter 15 a simple harmonic oscillator. It will oscillate back and forth just like a spring, just like a mass on a spring, oscillate back and forth, like following a sine or cosine curve to describe its position. So part E, we've got, I'm going to say the object will be in simple harmonic motion. And I think that's really all we need to say about that. I can check the rubric, see what they were looking for. I don't know if they were looking for more math there. If they are looking for more math there, we don't have access to that until chapter 15, so I'm going to leave that out for now. And then part F, write an equation that could be used to calculate the time it takes the ball to move from point P to the center of the planet. And it's not necessary to solve this equation. This might, I believe, also be getting ahead of ourselves. So I'll give you just a sketch of the idea, and I think this is probably what they're expecting you to do. You just think about that for 1 second. Because, yeah, I think it is going to have to go in this direction. So this is a little bit of chapter 15. We know that if force is equal to negative CR, that's like force equals negative KX. Well, force is equal to mass times acceleration, negative CR. And then acceleration is the second derivative of position. So you could write that as mass times the second derivative here would be like that, right? So dividing both sides by m, like that. And then we talked about, I think we might have mentioned in class the other day, that what kind of function is has a second derivative that's the negative of the original function. Well, it turns out that that's going to be a that this is a sine or a cosine function that you use. And the convention is to use a sine function, although it really doesn't matter. So there are a couple more tricks here that we can use here. It turns out that this thing here, the square root of this, is equal to what we call omega, which is the angular frequency, which is that. And the reason we do that is if you start back here, if you start here and say, okay, well, I think that means that R is equal to the sine of t. right? But it's not just sine of t. I mean, that would certainly, when we took the two derivatives, I'd have dr dt is equal to cosine of t, and the second derivative would be equal to negative, sorry, I should give myself a little more room there, negative sine of t. I'm going to use that as part of a fraction in a second, of t, right? I mean, that gives us this part, right? That r is equal to this, and its second derivative is negative of the same thing. But what's supposed to be here? Like this thing, this is the amplitude of the sine function, and we know that as this thing, in this case with the planet, as it oscillates back and forth, the amplitude of that oscillation is the radius of the planet, right? As it goes from here to here to here. So that amplitude in this case would be r, capital R. But what's the thing that goes in here? Well, if you look at what's happening here, we need something, when we take the derivative of what's inside, it's going to pop out, and then it's going to pop out again. So whatever's here, the c over m, we need to have the square root of it in here, right? Because then, when that pops out the first time, r times the derivative of what's inside is going to be c over m. And then when it pops out the second time, we need to have minus r times c over m times, and then in here you have that, right? So that's what we're looking at. That's what we want. So what is this? We call this angular frequency. And we know from our pre-calculus days that period is equal to 1 over that. So period is equal to the square root of that. So that is the that's the equation, I think, that they're looking for there. But again, I'll look at the rubric and see if that's what they're interested in. And that's just kind of a preview of some stuff that we'll do in Chapter 15. All right, let's do the next problem. So in Part A, they want us to, if the radius of the planned orbit is r, use Newton's laws to show each of the following. So they want us to use Newton's laws to show that velocity is equal to the square root of g m, mass of Jupiter, over r. Well, we know that equation. We just have to derive it here. So you could look at your notes, I guess. But we know that this started from gravitational force is equal to g m m over r squared. And we know if the thing's moving in a circle, that centripetal force is equal to mv squared over r. Right? Where r is the radius of the orbit. And so, setting those two equal to each other, we get g m j equal to mv squared over r. One of those cancels, one of those cancels, so v is equal to the square root of g mj over r. That's, you actually need to go through those steps to get the point for that. Even if you already know that formula, you can't just state the formula. That's not showing anything, since they gave it to you. And then they want you to also show that the period is equal to, basically that's Kepler's third law solved for t. So we just have to take this a step further and say that we know for simple harmonic motion that velocity is equal to 2 pi r over t, or in other words, that t is equal to 2 pi r over v, right? So that you can square. I think it's actually easier to square both sides first, or I don't know how you want to do this. There's a bunch of different ways you can get there, but you could do it like this, I suppose, over the square root of GMJ over R, just substituting that. And then you look at what they want it to look like, and you notice that everything's under a square root sign. So to get the top under the square root sign, I just have to say, well, 2 pi R is the same as the square root of 4 pi squared R squared, right? And then dividing by a fraction is the same as multiplying by its reciprocal. And that gives you the square root of, putting it all under one big square root sign, 4 pi squared R cubed over GMJ. So one way or another, they want you to derive that result. Okay, and you can expect to have to do that somewhere in the on the AP test. Okay, part B. The explorer wants the satellite's orbit to be synchronized with Jupiter's rotation. This requires an equatorial orbit whose period equals Jupiter's rotation period of 3.55 times 10 to the 4th seconds. And they want to determine the required orbital radius in meters. So we know that, using Kepler's third, that period squared has got to be equal to 4 pi squared over g times the mass of Jupiter, which is 1.90 times 10 to the 27th, times r cubed. So they just want us to solve for that. Suppose you want me to do that. So let's see. What do we need to do here? Solve this ugly looking mess. So we have let me just check and make sure I've got my G in here. G. Yep. Okay, so I have 3.55 times 10 to the 4th squared times, times G times 1.9 times 10 to the 27th. All right, that's all the stuff that's going to be on the top. And then divided by 4 pi squared. Make sure you have that in parentheses. And that gives me, that's r cubed when I have that. And then I want the cube root of that. So math number 4 is cube root of that answer. And that gives me that, which I will report as 1.59 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And that looks like a reasonable answer because it's more than Jupiter's radius. Of course, it couldn't be inside the planet. That wouldn't make any sense. Let me just check that again and make sure. So I move the decimal. 1, 2, 3, 4, 5, 6, 7, 8. That's correct. Okay. And last part I'm going to do on this sheet itself. Suppose that the injection of the satellite into orbit is less than perfect. For an injection velocity that differs from the desired value in each of the following ways, sketch the resulting orbit on the figure, where J is the center of Jupiter, the dashed circle is the desired orbit, and P is the injection point. Also describing the resulting orbit qualitatively but specifically. So qualitatively means in words, not with numbers, versus quantitatively. Okay. So when the satellite is at the desired altitude over the equator, its velocity vector has the correct direction, but the speed is slightly faster than the correct speed. Well, if the speed's faster, that means if the speed was really, really fast, it would just escape completely, right? If it's a little bit too fast, then it's going to escape and, oops, that is a pretty lousy looking ellipse. That's supposed to be an ellipse, where that would be at one of the focal points. So I'm going to say here that this is an elliptical orbit. With J at the near focal point. And then if the velocity has the correct direction but the speed is too slow, then it's going to be also be elliptical, but J will be at the other one, right? It's not. It's going to get sucked closer to the planet because it's not going fast enough to have its nice round orbit. So I'm going to call this an elliptical orbit with J at the far focal point. There you go.